Okay, so this is the presentation for Research Project C. So I'm being supervised by Katie and Paul. So Paul can't come in today, but hopefully you can see the recording. So I'll go through an intro and a quick recap into what we did last trimester, intro into some of the stuff that we need to know for this presentation, and a recap of the literature review that we've done. So last trimester we went through random geometric graphs, so this is going to be a main focus point of the presentation because this is the graph model that we're using. And so if we want to look at some examples of where a random geometric graph might be useful, in a real world application we might look at wireless networks. So if we have, for example, some laptops which are connected to the same system, and then the positioning of those laptops might be random, we don't know where they are. Let's say, for example, students own laptops, they're moving around, and there's a Wi-Fi network or a radius around each. And if they're within a certain distance of one another, we draw an edge between them. Now, we'll go through a brief overview of the stuff that we need to know for random geometric graphs. So, we've already spoken about placing the vertices or the movement of the vertices. We like to think about them as placing vertices in a metric space, and then drawing the edges between any of the vertices which are close enough to one another. We commonly use either a Poisson or uniform distribution. There are some other distributions. You can weight distributions to certain sides or to certain areas of your metric space depending on what you're trying to model in the real world. But most commonly we use one of these two. We'll be using a Poisson distribution, and we'll use the notation G and A for our RGG. What this means is we have a square of size n. The A is the area of the circle around each vertex. And we're using a Poisson distribution with a density of 1. So what that means is we expect n vertices to be in our metric space. We're not going to get exactly n vertices each time, but around that much. And we also want to look at the evolution of the random geometric graphs. And the evolution, the way we think about it, is introducing edges in order of increasing length. Okay, so with all our vertices, the area around each one starts to grow. And of course, the way we add our edges in that instance is in increasing order of length. Okay. Now we'll look at rigidity theory really quickly as well. So the intuition you get of the word rigid in the physical world is exactly the same intuition we use in the mathematical world. Okay, so we have many practical applications, engineering, robotics, those are clear. If we have a truss bridge, for example, that's rigid. Engineering, robotics, we want rigid components. We might have flexible joints, but we want rigid components in robotics, for example. Material science and medicine, biochemistry. Sometimes in materials, we want to look at rigid nano materials and what they're made up of should be rigid. Now for rigidity, what we're going to look at is a D-dimensional framework. So what that is, it's a pair G and P. G is our random graph. Well, sorry, not our random graph, which is our graph. P is the embedding of the vertices of the graph into some metric space. Okay, and the metric space is usually it's D-dimensional. It's usually Euclidean space. And we ask questions when our framework's D-rigid. So when our framework's rigid, it's when we look at the motion of the vertices, a continuous motion of the vertices, and if the distance between the points which are adjacent to each other are maintained, while also maintaining the distance between every single other point for all continuous motions, then it's rigid. D-rigidity looks at D-dimensional rigidity. But what we're going to do is we're going to simplify our problem by looking at generic embeddings, because what happens with generic embeddings is that we don't actually care about the framework anymore. We just care about the graph itself. So we're not worried about this pair, we're just worried about the graph. So it simplifies the problem. So now we can look at our random geometric graph and just focus on its properties, which makes it easier for us. And so our motivating question for the topic is when are random geometric graphs rigid? This will be what we're trying to explore for this project. And so this is a nice brief intro to the two topics we need and why we study the two of them. Now a recap of trimester 1. What we did was we completed a literature review of everything we need to know about random geometric graphs and rigidity theory. We understood the LNPR result. The LNPR result, I've just made an acronym out of the authors' names. And they have a result for random graphs, not for random geometric graphs. But they have a result for random graphs, and so we want to understand their proof to see if we can modify it for our own purposes. And that's what we started thinking about at the end of T1. Now, in the literature review that we did, there's some results which I think are quite important. Throughout this presentation, I'm going to be putting up the maths onto the board, if that's a thing. I'll explain the intuition, I think that's a bit easier to understand, but the maths is here if you like. This first result is a random graph result, okay? And it talks about the hitting time of two graph properties. Those properties being K connectivity and minimum degree of at least K. And what this result is telling us is that with high probability, we know that those hitting times occur at the same point for random graphs. Okay, so that's what this result is saying. Now there's another result which we found for RGGs. The notation here is a little bit different, okay, but essentially the idea is still the same. It's saying that with high probability, those two properties have the same hitting time. And this is for random geometric graphs. Now why are these two results important? Why am I highlighting them? Well, the idea is the first result came for random graphs, and then someone came along and said, okay, we have this result for random graphs, can we do the same thing for random geometric graphs? And was able to prove that it's actually the same. So the question for us is there a result for random graphs which we can modify for our own purposes? And that's where the LNPR result comes in. And they have another hitting time result. The two properties they look at is D connectivity, a minimum degree of D, or they're interchangeable essentially because they're both equivalent with high probability, but they look at a minimum degree of D and D rigidity. And what their result is that for random graphs and with high probability, those two hitting times are the same. And so essentially, we have our conjecture, and our conjecture is the same result as the LNPR result, except now we're modifying it for the RGG graph model. And so we've overloaded the notation here. If you were paying attention to the math, we had this curly F for a point set. Now we've got the curly F for a random geometric graph. But once we figure out the result, we'll try to formalize the notation and do it that way. But essentially, we're just saying that for random geometric graphs, the hitting time for a minimum degree of D and D rigidity is with high probability the same. Okay, so that's a quick intro and a recap of everything we've done so far. Now we're going into the main results and the work we've done this semester. I'm going to recall the plan for trimester 2, just to show you where we've sort of gone along with the plan, where we've gotten up to, if we've changed anything along the way. And so the first thing we wanted to do was to understand the LNPR result, the propositions they used, the proofs they went through. We wanted to modify those for RGGs. We believe we could do this because of the idea that we saw this other result for random graphs and how they were able to modify that for RGGs, so we thought maybe we could do the same thing. And if possible, we were going to do some experimental techniques, explore that to see if we can come up with conjectures or highlight anything that's worth highlighting.
All sounds familiar.
All sounds familiar? Okay, good.
Still some
Yeah. But yeah, so this is the LNPR result. I sort of condensed everything that we had last trimester into one slide. I'm going to gloss over these last two because these aren't too important for our purposes at the moment. But the first two, so the closure and the proposition 1, are quite important. So the closure, I'll quickly recall what that means. So the closure sort of looks at the local areas of the graph which are rigid. It looks for local points of rigidity. And so the closure contains every edge which is already in our graph, but then if you find an induced subgraph of our graph which is rigid, all the edges that can exist there are also included in the closure. So you can imagine if our entire graph is rigid, then the closure is just every single edge that's possible. Now, the first proposition from the LNPR result is that if we have a certain number of edges, now this notation as well is for, so this is a random graph result. It's important to remember that because this notation looks very similar to our RGG notation, but this is actually for random graphs with n vertices and this number of edges. So they're essentially saying once our random graph has a certain number of edges, we can expect that the closure should contain at least 5n/9 vertices. So what they're essentially saying, in other words, is once they've got enough edges, we can expect that there exists some induced subgraph on about on exactly 5n/9 vertices, or at least 5n/9 vertices rather, which is rigid. Now, we looked at the proof of this proposition. This was our first step, our first attempt at sort of getting somewhere with proving our conjecture. And so we looked at this lemma. This was something that was required for their proof. Now, we had to understand this, and we had to look at what they were doing, and a part of the proof technique at some point, they looked at sampling edges randomly based on a vector of real numbers between 0 and 1. So they had this vector, and all the elements were between 0 and 1, they were real numbers, and according to some equation, they would see if the value was less than that equation or that expression. If it was less than, they would sample from outside of the closure. If it was greater than, they would sample from within the closure, but edges which we haven't picked yet. So that was sort of our way of sampling things for this proof. Now, we immediately ran into a roadblock with this one, because the question is, how do we sample edges in a random geometric graph? So the problem with that is, we spoke about the evolution a little bit earlier, and the evolution is sort of locked in place. Once we've got our vertices in our metric space, we can't randomly pick new edges, because that's not how we evolve RGGs. The evolution of random graphs works that way, because you can think of it, if we haven't picked an edge yet, we just pick randomly from the ones we haven't picked. But for an RGG, the vertices are locked in place. So we can't do that, we can't choose random edges. Can we add a new vertex somewhere into our metric space? Maybe that's the evolution. But well, we can't guarantee that always introduces one edge, but also it increases the upper bound to the number of edges that we can have in the graph. So neither of them really seemed to work, nothing promising came to mind, so we had to dismiss this idea, which was the plan from the beginning, and move on to something else. And this was the second attempt we looked at. So the second attempt was understanding a result from Walters for hitting times of random geometric graphs. Now, if you had a keen eye, you would have seen earlier that the hitting time result we had on the slide for D connectivity and min degree D was by Penrose. We're looking at Walters here though. So Walters actually has the same result, and it proves the same thing. K connectivity and minimum degree K with high probability have the same hitting time. But his proof was looking at a specific case. The first case he looked at was just connectivity and no isolated vertices. And so we tried to understand the proof, and we looked at the connectivity result. And what we found was, the way he did it was he leveraged an already existing result, which was that the hitting time for no isolated vertices was log n for the area around the vertices. And the proof to show that the hitting times coincide was split into two parts. So the first thing he did was show that the random geometric graph with an area of n, the metric space having an area of n, and the area around each vertex being C log n, is very unlikely to contain two relatively large components. Okay? And the second part was essentially saying that an RGG with an area a little bit smaller than log n, in particular this graph, must only contain large components or isolated vertices. So you can already see, putting them two together, what's essentially saying is that we can't have two or more large components, but we can only have large components or isolated vertices. So already you can sort of see where he's sort of going with this connectivity proof. But let's do a bit of a deeper dive into both of these parts. So we want to look at this lemma. So this lemma is just sort of formalizing mathematically the first part of the proof. And the way he proved this, so again, the math's up here if that's your thing, but I'm going to sort of explain the intuition about how he went about proving this. And so he used the tessellation argument. So we've got our metric space, we tessellate it with squares, and we're also, proving this by contradiction. That's important. So we're assuming that two large components do actually exist. So we've got these two large components in our metric space. We've tessellated the area. And what we're saying is, because they're large, those components, they themselves must meet many tiles. So what we mean by that is, if we take all the tiles which either have a vertex or an edge of either of the components, that's how many tiles that those components meet. All tiles adjacent to the component are empty. Why is that the case? Well, the tessellation we've picked is such that any two tiles which are adjacent, as in they share an edge, two vertices on either side must be connected. So they must be empty the adjacent tiles. Otherwise, those components aren't components, there's a bit more to them. Now, because the components are large, there must be many of these tiles. And because there's so many, it's quite unlikely that the probability that they're all empty is very small. It's quite unlikely that will happen. In fact, the probability goes to 0. So then we can say that it's never going to be the case that we have 2 or more large components. This following lemma formalizes the second part. Again, the math is up here, but we'll speak about the intuition of the proof. Again, we do a proof by contradiction by assuming such a component can exist. What I mean by such a component can exist, so this lemma is the one which is claiming only large components can exist or isolated vertices. We're going to say, okay, well, let's assume a small component can exist. And now what the proof does is, well, the first step is we're saying, well, we're going to assume a small component can exist, but we'll show that it can't be too small if it were to exist. So that's the first thing we did, or the first thing Walters did. And then, this is a nice diagram, we'll go into this diagram in a second, but we're saying that, supposing that this component does exist, which we're calling H, we're going to take this R, which is the smallest area rectangle, which makes tangents to the vertices of the component. And the tangents must be horizontal and vertical. Okay, so you can imagine that this is sort of just the smallest area rectangle that can cover everything in the component. And now what we have is, we're looking at this shaded region, which represents the minimum area required to be empty, such that this is an isolated component. Because you can imagine if any vertices exist around in the shaded region, they must be connected to R, so it's no longer its own component. And the way the circles are drawn are such that this is actually the smallest area possible, because you can imagine that we should have 4 vertices on the boundary, 1 on each edge. But if in the, there's a 0 probability case where we only have 2 vertices on the boundary on each corner, and this represents the minimum area that they can possibly cover.
And they're the centers for those circles.
That's right.
Right, okay, got it.
Yeah. And so with this minimum area, of course it's going to be larger in practice, but what Walters then shows is that the probability that this area is empty also goes towards 0. So then again, we can say that this is impossible to occur. So we can't have a component which is this small. And so this is the proof for the second lemma. The roadblock we ran into with this one, though, is that how do we apply this to rigidity? How do we modify these proof techniques? How do we use them? Well, we can prove one rigidity at least, but this is quite trivial because one rigidity is just equivalent to connectivity. And empty tiles actually don't really tell us much about rigidity. So Walters went around each component and looked at the probability they were empty. This doesn't really tell us much. It says a lot for connectivity, which is good, but it's not exactly our property. What Walters does mention, though, is that similar techniques may be used for K connectivity. He doesn't actually provide the proof for it, though. And his lemmas are for the connectivity case. So it's hard to sort of translate it over. So again, we have to shift our focus a little bit and see if we can figure out how to prove it for K connectivity. So we track back and look at Penrose's hitting time result. Again, the result is the same, but we thought maybe we could understand how he approached his method for proving this result to see if we can modify it for Walters. And so the result's the same, but the technique is completely different. What Penrose does is he approaches it with a probability theory approach. That's his style. And so we sort of immediately ran into a roadblock with this one, in that we hadn't studied anything about probability theory before in T1. So looking at his papers were quite difficult to understand. His textbook as well was extremely hard to read. I can see you nodding, so.
I didn't realise it was going to go this route.
Yeah, my steps is.
So we ran into an immediate roadblock. But there was one thing which was really beneficial about one of his papers, and it's these 2 propositions. Again, the maths is up here. Took a bit of time to understand exactly what's going on with these 2, but once we got around to it, what we realized was that these are actually generalizations of Walters' lemmas. So this helps us a lot. These two help us understand the specific case of connectivity, how Walters used these two for his own purposes, but then also how can we use these two for the K-connectivity approach of Walters. So we didn't want to go the probability route, but we needed these to then go the geometry route. And that's what we did. So that's why this is attempt, I haven't been following with the attempts, but this is why it's attempt 3.5, because it's sort of a combining of the two approaches. And so we want to put the two results together. We've now got the generalized versions of Walters' lemmas. We also know in Walters' textbook, in the chapter in one of the textbooks, he gives us a threshold for K connectivity. So we know this threshold, but how do we actually prove it? Well, that's what we did. We generalized Walters' lemmas and proved the two connectivity case. And so on this slide, what we're doing is we're modifying those lemmas for the two connectivity case. I'm going to explain the intuition behind these rather than going through the math over here. But the intuition is that initially we spoke about those two large components, which must be empty in their boundaries. Instead, the way we look at it now is those two components, what's the probability that exactly one vertex exists in their boundaries? Or rather, another way of saying that is, what's the probability that a one vertex separator exists between those two? Of course, the specific case of that for connectivity is, what's the probability a zero vertex separator exists? But that's not really how we worded it. So understanding it now that way helped us come up with this lemma. And it also helped us come up with the other lemma, and in a similar style, it's saying the exact same thing. We're looking at single vertex separators and saying, does a single vertex separator exist which gives us a small component, and proving that it's impossible. And those are the two modified lemmas that we came up with for two connectivity. And so this is essentially saying the same thing which we've already gone through. So we're looking at the single vertex separators for these two lemmas and putting those together to get the two connectivity result. And I'm going to go through some of the proof techniques we use here, some things that we ran into which were a little bit different than the connectivity case. Well, initially, so for the first lemma, the idea is the same. It's that we got these two components and we're trying to prove that their boundaries only contain one vertex, or exactly one vertex. Now, the caveat with this is that these two components, they only have a small intersection of tiles where the single vertex separator can exist. Because of course, if we have the two components here, and the single vertex separator exists on like the top left of this component, it doesn't really make sense to consider all of them. But this doesn't actually change our maths much because this is an even smaller instance. So we can prove that for any of those tiles, if the probability that exactly one vertex goes to zero in any of those tiles, then we've proven it for this small instance of this small crossover of tiles which actually matter. For the second lemma, idea is also quite the same. So we're showing that the rectangle that we draw around our component and that shaded region must contain exactly one vertex. The caveat with this method though is that we get some additional logarithmic terms in our probability expression, but again, sort of working through the maths, figuring out the algebra, they all sort of disappear and you realize that the probability still goes to zero either way. So there's it's a bit more involved, the maths we use, but otherwise the techniques are really quite similar. Once we've understood the generalized lemmas, we were sweet. And so, I've gone through the presentation quite quickly, so hopefully I didn't gloss over anything too much, but we're up to the next steps now. So essentially, we've proven the two connectivity case. Something else which we should consider is that it still applies for the K connectivity case. So the techniques are really similar. We've always got that constant factor. And proving either of the lemmas for some constant K is exactly the same as proving it for two, with a couple of different terms which you have to account for. So we've now proven the RGG result using the geometric approach which Walters took. And so that was a really good step forward for proving what we wanted. The reason why is because, well, the question is we want to ask is where to from now? What are we going to do? Well, we've got all these proof techniques, all these things that we've understood, and we now need to think about how we can apply them for rigidity. And that's sort of where we're at. And I'll go through some of the ideas we currently have. So some potential ideas, we're looking at a similar style to Walter's argument. We want to prove that with high probability, each of our tiles have at least 2 vertices. Why at least 2? I'll go into that in a second in the next slide. We could also think about it in the opposite sense. So coming back to this first point, the reason why looking at the probability of 2 vertices might be tough is because I haven't seen a proof where they've shown that the probability of this goes to 1. So rather, why don't we show the probability of things going to 0 of things that don't guarantee rigidity? So this will guarantee rigidity, but what about proving that the stuff that doesn't guarantee rigidity goes to 0? So that's what this point is saying. Another idea though is, could we pair every vertex with all other vertices within a specified distance? So the reason for that is, it's similar to this point up here, which again I'll go into in the next slide. But if 2 vertices are close enough, then they must be connected. And then any other vertices which are also close enough to those 2 must form a rigid component. So if we can pair up all the vertices which are within that set distance, so they share an edge and also have a range around them where any vertex within that range forms a rigid component, then if this sort of pairing covers every vertex, we've potentially proven rigidity that way as well. So that's another idea. Now going to the first point, here's a bit more definitions we need for rigidity. I've put them at the very end though, because this is sort of where we're at, and this is the thing I've looked at the most recently. And so we're looking at these 2 specific construction moves, in particular the first one, but we've thought about the second one as well because it still does help for our purposes. It just seems a little bit tougher to use. But the construction moves, what we have is, we add a new vertex to our graph, and its neighborhood, so its degree is 2, and its neighborhood are 2 vertices which aren't the same. So essentially we're just saying that we add a vertex and it's got 2 unique neighbors. Or if another construction move is, we remove an edge that already exists between 2 vertices x and y, which are different. We add a vertex with a degree of 3. It's connected to those 2 vertices which shared an edge already, and some other vertex z, which is part of our vertices. And what we call these 0 and 1 extensions, respectively. And a theorem we're using, it's not worded exactly like this. This is sort of a compilation of 3 other nice theorems. But the idea is, given some graph G, which is rigid, performing either of these moves doesn't destroy rigidity. So how do we leverage this result for our purposes? Well, the idea is, if we can show that we have a rigid component in some part of our RGG, and every other tile is just a 0 extension of that rigid component, then it must be the case that we end up with something that's rigid. And so that's the point, idea 1 from the previous slide. Idea 2 is something that seems a bit more workable. So the reason why I say that is, in the Walters proof, he uses this lemma, which, so we spoke about those 2 components, and the number of tiles they must be connected to must be large, and the probability that all those tiles are empty goes to 0. Now, instead of looking at it that way, why don't we look at the probability that those tiles contain 1 vertex each, okay? And so I'm trying to use a lemma to figure out what number of tiles can't we have which have 1 vertex each, which are diagonally connected. That number actually goes to 16, if my math is correct. So that's something that I'm going to revisit. Yeah, so this is new. I'm going to talk
diagonally connected means at the particular corner and it goes diagonal, right?
That's right. And so I'm pretty sure the number goes to 16. So what that means is we can only have 15 tiles diagonally connected with at most 1 vertex each. And so the idea is, I could have drawn this, but
there is a pen here.
There is a pen? Thank you. Thanks. So we've got 15 tiles in the worst case, which have, let's say, at most 1 vertex. So they could have 0, could have 1. If it's sort of a taut string of those tiles, then that's the best case scenario. Because since they're 15 connected tiles, every tile around them must have 2 vertices at least. So in that case, those 15 tiles must be 0 extensions from the other tiles surrounding it. So the worst case is when it's all clumped together as closely as possible. Right? So if they're clumped as closely as possible,
No,
I think I've got. Hold on, I think I have some here actually. Yeah. Yeah, I do. Okay. I always bring them for teaching. Okay.
More organised than me.
Okay, so let's say we have a 4x4 grid. And then this is part of our tiles which contain 2 vertices, right? Because this is 15. And so, let's use
Okay, so your result is in any 4x4 grid at most 15 of the squares contain at most 1 vertex.
That's right.
Or exactly 1 vertex.
At most, 1 vertex. So they could be 0, but yeah. And so what we know is that because it's only 15 which can be connected, then assuming that this isn't at the boundary of our component, this area here is filled with tiles which contain 2 vertices each. So our safe tiles are these ones. Because anything in these tiles must be, if there's a vertex in any of these tiles, they must be a 0 extension from these tiles out here. Okay. And so the only 3 we really have to consider is these 3. And so now this is the point of just, I guess, research and ideas. This is where I'm at. And I'm trying to think about, can we prove that the situations which don't guarantee rigidity can't possibly exist? And so I thought about maybe the instance where these all contain 0 vertices and there's like a vertex each here, but that can't happen because we know it's connected. The graph must be connected. So if a vertex did exist here, then maybe something exists here as well, which connects this way. But this also causes a problem because if it's only connected to this one, this is flexible about this connection. But at the threshold of 2 connectivity, that's also the threshold for min degree 2. So it does have 2 points of connection. So now I'm just sort of like free flowing with ideas. I haven't thought further than this, but I think there's something here. I think we can. I think we can prove the 2 rigidity case with this, if my calculations are correct about the 15 tiles.
Yeah, I need to check this now.
Yeah. So, yeah. Okay. That's the ideas part. So we'll come back to the presentation. And so, just to wrap everything up, a conclusion for the presentation, closing thoughts about the project as a whole. So unfortunately, we weren't able to prove the conjecture. So we wanted to focus on the 2 rigidity case. We think we can prove it for D rigidity, but first we want to start small and go up from there. But we haven't proven it yet. So the idea is I'm going to keep researching. I think we're close, and I've really enjoyed the topic. I think we've built the correct sort of arsenal of mathematical tools to use to be able to prove this. So does this make the project a failure? Well, I don't think so, only if we stop, right? If we stop now and say, oh yeah, we tried our best, then it's a failure, but we're going to keep going. I think we can prove it. But regardless, I'm still glad we took the project. There's so much that I learned about a whole range of topics, in particular graph theory and a bit of probability theory, which I wasn't expecting to do a whole lot of probability stuff, but trying to understand pen arrays, you have to learn some probability along the way. There's matrix theory, geometry, combinatorics, and yeah, our work isn't done yet. I think we're still on track, and hopefully we can prove it. And so, yeah, any questions?
Thank you very much. Can you go back one slide?
Yes.
I'm just going to make a note of time. So I think your 3rd dot point means even if you do stop now, the project isn't a failure. Like if you're going to do research, some stuff isn't going to work out, and it's disappointing, but you kind of take it and go, all right, next please, So I think absolutely not. And I also remember thinking last term, wow, that's ambitious.
Yeah, sorry. I guess you're not familiar with the probability side of things.
Well, I I just think random geometric graphs are scary. But,
Yeah, I haven't touched them before, so I saw the Erdős Remy proofs, like, oh, they seem not too bad.
Yeah.
I really underestimated the step up in difficulty.
But so I think seeing the tiling stuff come into it is nice because that brings it back to something a bit more discreet and manageable. And so I think it's great that you adapted that stuff. So you proved the two connected.
That's right, yeah.
Result. And
Or was it K connected?
you think it should work for K-connected, or you're still checking, or it does work? Or?
Well, I guess I sort of assumed it does work because, in Walter's textbook, he mentions that the techniques are the same. But now that I think about it, I did the two connectivity case. I didn't keep in mind to test K-connected. So I think what I might do before I submit the report is actually double check the maths myself instead of just going, oh yeah, Walter says it works, it's fine. I'm going to go through and say, do the constants actually just like, are they always constant factors? So I'm going to put K in instead of 2,
right,
and then test that out, and I might include that as like a final section at the end of the proof saying, here we go, it does work.
Sorry to relate to that. If you go back to slide 22,
Slide 22.
you talked about one connectivity and one rigidity being equivalent. Can you remember why we thought there was this connection between K connectivity and rigidity, especially the 2 dimensions? I think I mentioned it once, but I'm not sure.
Oh really? Wait, why we think there's a connection?
Yeah.
Oh,
No?
I'm not sure, no.
So in D dimensions, D connectivity is a necessary condition.
Yeah.
And in 2 dimensions, we know that 6 connectivity is a sufficient condition.
Yeah.
So in 2D, we know that the hitting time will be...
6 connectivity implies rigidity in 2 dimensions.
Yes. Cool. So yeah, in 2 dimensions...
So you might get some rigidity out of this if you can do K connectivity.
Yeah, exactly. And also just like, we already know that the hitting time for 2-dimensional rigidity is sort of lower bounded by the 2 connectivity hitting time and up bounded by the 6 connectivity hitting time. So motivated by that, it seemed likely that these K connectivity proofs would maybe be adaptable.
Can you say the first one you said again? The D connectivity is a necessary condition for rigidity in D dimensions.
Yeah. So in 2 dimensions there's 2 connectivity.
Right. Great.
So yeah, in all dimensions we have this necessary condition, but the sufficient one is only known for, I guess, 1D and 2D.
Great. I didn't write down slide numbers.
I can go, I know where they are.
This is that's okay. With your 15, it would it be obvious then? So I was, I think I was following the general kind of ideas that you were saying, but when you talk about having one vertex, was it like, maybe I should draw pictures. When you have a cut vertex, like a separating set of size 1, so you've got a blob here and you've got a blob somewhere else. And when you're talking about one vertex on the boundary, was that on the boundary of a little like tile or rectangle, or could you just say a bit more about that?
Yeah,
I'm trying to picture it.
Okay. Yeah, so we've got our 2 components.
Yeah.
So I'm going to just draw them as circles. And then we've got our tessellation. And so...
This is after you've deleted one vertex.
No, so this is throughout the proof, I guess.
So if you have two rigid components, is that what you're saying?
Is this for the...
I was thinking of the 2 connectivity extension of that.
Yeah. So we've got our tessellation. I've drawn it pretty badly. This should be connected here. But so they're a bit close as well, but imagine that they did have... so this is part of the boundary of both. This is also part of the boundary of both.
Right.
They still have other stuff which is in the boundary. So this is in the boundary and like other stuff up here and so on. But the question is, what's the probability that this boundary here, which intersects between the 2 components, contains exactly one vertex, which is that single vertex separator? Now, the probability for all of these, so everything in the boundary, all of these ones like around here, actually goes to 0, which subsumes this case.
Those circles might not be connected components of the graph. It's stuff that you've got, but then they might be connected to more stuff.
No.
So how do you get this one vertex in the... I guess I'm confused. I'm still confused. The two blobs, if they were connected but not too connected, they'd have a vertex in common, right?
Yeah.
The cut vertex. Right?
Yeah, that's right.
So then,
Yeah, go for it.
wouldn't it look more like somehow you've got one vertex? Like, isn't that a?
Oh wait. Yeah.
So,
Yeah, I get what you're saying, but I think that this, yeah, so the proof is saying that it's two connected. So this doesn't ever happen, so there must be two vertices. But I guess with this example, because the way I would have thought about it intuitively is like, oh sorry, that was horrible. Let's say like this. And then same thing up here.
Right. So there are other things that could be in the graph that aren't in those two circles.
I think it would just be the single vertex.
Right. Yeah, that's fine. I get it. Yeah.
Okay. Yeah.
So it's like after you delete
Yeah. After you delete
the
the
separating
vertex.
set, what's left?
Yeah.
Yeah. That's what I wanted to clarify. Okay, great. And if you had then the 15 tiles,
Yeah.
is it obvious that the missing one would be on the outside?
Oh no, that's a really good question. So it's not obvious that the missing one would be here, but if we did have 15 tiles which were connected like this, then this is a very this is our best case scenario, because if all these tiles in the boundary have at least two vertices, then these are already covered, 0 or 1 vertex each. So if they're in it like a taut line, that's fine. If they're a bit closer together, also pretty fine. The worst case is when they're sort of clumped together. This is when it's like hardest to guarantee rigidity.
Isn't that interesting?
Yeah, and so yeah, the point is, can we prove that anything that doesn't guarantee rigidity can't ever occur with the properties that we know? So min degree 2 connected.
Right.
These, and again, I'm making a huge assumption that this isn't on the boundary of our component. So I'm assuming that these tiles actually contain something.
Yeah.
Because you can imagine if this occurred right on the edge of our tessellation, it'd be hard to deal with these.
Yes.
But yeah, again, it's still at the idea stage. So.
I guess this connects to why we're looking at the torus rather than the square.
Absolutely. So
Yeah.
you can easily just get something at the end and go move around. You said in the two connectivity proof where you were adapting Walter's proof, there were these logarithmic things that cropped up, and then you have to really carefully calculate the constants and show that everything cancels, or how did you get rid of those?
So I looked at the big O notation of everything, and you get like this really weird, I can't remember off the top of my head, but there's like square root log n, double log, and all these things, and then you just have to cancel everything out. In the report, I've put a lot of the maths, I haven't left it like to the reader, I've put a lot of the steps to show how you can bring it down to little o of 1.
Okay.
And so, there's like with algebra and stuff, you can just sort of cancel everything
Right,
out.
and I get to see that at the end of the week.
I hope so.
Yes,
Yeah.
The submission deadline is Friday.
Friday.
Lovely.
I'm not sure what time on Friday.
6
Probably,
p.m. I think.
late. Yeah.
And
That's fine. Good. I look forward to having a look at it.
yeah. The report's really good. Oh, that's alright. No, I was like, so the.
You may as well market it.
No, but yeah, because I explained just the intuition in the presentation. I think the report's nice because I should say, instead of the report's really good, it's nice because I get to show the maths.
Yeah, you have the space to explain things properly. Yeah, absolutely.
Hopefully it's not too dense. Hopefully it's not like pen roses.
Well, yeah.
Yeah, good work on understanding that.
Yeah.
Absolutely, what a nightmare. But yeah, it is interesting to see the range of techniques that get applied sort of in the one area. It's probably Penrose's book that made me scared of.
I mean, I looked at it and thought, oh my god, I don't want to touch this.
Yeah.
And then I contacted a friend who sort of works at the boundary rigidity theory project. And he was like, yeah, I can't understand that. Okay. So when he went away and understood it, that was a real shock.
Yeah,
Yeah.
impressive.
I mean, to be fair, I didn't understand the paper.
But
It was
you
just
found
the
the right
proposition.
results.
All you
Yeah, I found
need,
that
all you
result,
need to do is, this is what I need.
Yeah.
I'm sure someone's checked that this works. It doesn't have to be me.
That's right, yeah.
Yeah.
I don't care about the proof.
Yeah.
I'm just going to use the
I'm
propositions.
just going to use this tool.
Yeah.
Absolutely. I have no further questions, I think. Yeah, nice.
Yeah,
Yeah, thank
really
you.
well done.
Thank you.
It's
Yeah,
a
good
huge
work.
achievement in just like 6 months.
Yeah.
Yeah, absolutely.
Okay, let's stop.
Excellent. Yep.